In this unit, we've been learning about nuclear reactions. We've already learned about fission and fusion. And now we're going to turn to another nuclear reaction called alpha decay. During alpha decay, a nucleus shoots off a particle, called an alpha particle, and it turns out to change what element we have. In this lesson, we're going to learn just how to predict what element we'll get after alpha decay. Let's learn. Do you remember the gold foil experiment we talked about at the beginning of class? Remember that what Rutherford did was he shot alpha particles at a gold foil to discover the nucleus. Well, at the time we just said alpha particles are these small subatomic bullets. But in this video, we're going to discover what exactly those alpha particles are. Let's take a look. Here is the symbol we use to represent an alpha particle. In the yellow is shown the mass number, and that's going to be the case through this whole video. We'll show mass number in yellow, and it's 4. So the mass number is yellow, and it's 4. That means there are 4 things in the nucleus. The atomic number here is 2. That means there are 2 protons in the nucleus. Now remember, the atomic number defines what element we have. And so if we have protons, we have an element. What element has the atomic number 2? Well, it turns out to be helium. We could go look that up on a periodic table. And so an alpha particle is just a helium nucleus. In both of these notations, whether you use the alpha, which is a Greek letter, or He, which is our symbol for helium, we mean this, a nucleus that has 2 protons and 2 neutrons. Okay, so when we take a look back at our gold foil experiment, it's shooting a beam of alpha particles at the gold foil. Basically, it's firing nuclei at nuclei, which is kind of funny. All right, and where do those alpha particles come from? They come from radium. So inside our little alpha particle gun here, we have a radium source. How does radium make alpha particles? It does it through radioactive decay. Let's take a look. So we start with radium, and we start with radium 226. So that means it has a mass number of 226, an atomic number of 88, and it shoots out an alpha particle. It's unstable, that means radioactive, and so its nucleus eventually falls apart and releases an alpha particle. The alpha particle shoots out. And if we have a bunch of radium, then we could have a whole beam of alpha particles. That's what we saw in our gold foil experiment. But we've already taken a look at how you have to balance nuclear reactions. The number up top, the mass number, has to stay the same before and after. And here you can clearly see that it goes from 226 to 4, so something has to be left over there. So that's the question we're going to take a look at now. What's left over when radium decays? And this will help us understand the gold foil setup, but also it will just help us in general to understand how we predict the products of a nuclear reaction. What's left over when radium decays? Well, I've broken this process down into 3 steps. What we're going to do is we're going to add up the mass number and atomic number before and after, and we're going to use the difference between those two to figure out what must be left over, what goes in all these question marks here. Okay? So let's do that. What do we have for the atomic number before? Well, 88. What do we have for the mass number? 226. Because there's only one reactant, one thing we start with. There's no adding necessary. And then for our product, we know that we have 4 for our alpha particles mass number and 2 for its atomic number. Okay, well, we can see it doesn't match. And that's going to help us, like I said, piece together what goes in these question marks. How will we do that? Well, if I had 226 things in the nucleus and 4 fell off, how many are left over? Right? This is exactly the same as you had 226 candy bars. That was way too many candy bars. You ate 4 of them. How many are left over? Same basic math here. And so what we're going to do in step 2 is take the difference. We're going to subtract the after from the before to see what's left. And we're going to write that as a separate product of our nuclear reaction. So let's do that. We started with 226 things in the nucleus. And then our alpha particle came off, leaving 4 that came from the nucleus. How many are left over now? 222. We can do the same thing for the atomic number. We started with 88. The alpha particle took away 2, and now we're left with 86. And so we're starting to answer now what must be left over. We know it has to have the atomic number of 86 and we know that it has to have a mass number of 222. But what goes here? What's its elemental symbol? Well, the elemental symbol we can find from the periodic table, because remember, 86 tells us what element it is. So that's step 3. We're going to look up the element on the periodic table by atomic number, and then we're going to write it down. So what's element number 86? Here's our periodic table. And remember, the number in the top right is our atomic number. It tells us how many things we have in the nucleus that are protons. Element 86 is Rn, radon. And so now I'm going to go back to my problem, and I'm going to write Rn as my isotope. So that means I'm left with radon. Awesome. So now we've predicted our first nuclear reaction products. We know that if radium shot out an alpha particle, it would leave behind radon. Here's the thing, you might have heard of radon before. It actually can cause radon poisoning. So it turns out that there's radium in the earth that's constantly decaying through this alpha decay and emitting radon. And that radon can seep up through the ground and fill places like basements. And if you inhale that over long periods of times, it can cause problems. And that's, again, because radon is radioactive and it undergoes alpha decay. So let's predict that product. So what are the products of alpha decay of radon? And I've given us a little bit more to do here because I haven't even drawn the alpha particle. So the very first step here is to draw an alpha particle as a product. Let's do that. So we're going to draw a forward arrow, and then we're going to say, okay, well, it makes an alpha particle. That means we're going to get out 4, 2, alpha. And our goal is now to figure out what goes in our 3 question marks. The way we're going to do that is, again, to add up the mass number before, which we know that our mass number before is 222, and our atomic number before is 86. All right, when it undergoes alpha decay, we know right now before we consider the other product, it has just 4 for the mass number on the product side. We'll put M number sign, and we have a 4. And then our atomic number on the products is 2. Okay, what must be left over? Well, we're going to need to take 222. That's our mass number. And here we're doing step 3, and we're going to subtract them just like we did before. We had 222, and we're going to subtract 4. And we'll get 218. Then we'll do the same thing with our atomic number. And we'll take 86 and we'll subtract 2, because that's how many protons are in the alpha particle, and we'll get 84. All right, so when we go to start to fill in our symbol, we know now that the top number is going to be 218 and the bottom number is going to be 84. We just need to figure out the symbol. Notice what's happened to here is, once again, the alpha particle has dropped the mass number by 4 and the atomic number by 2. And that's a shorthand a lot of people like to memorize, that the alpha particle drops our isotope's atomic number by 2 and the mass number by 4. So now my last step is to look that up on the periodic table. Okay, so what is element number 84? When I look for element number 84, I'll see that it's right there. It's polonium. So when I come back now, I'll be able to write down that the element left over is polonium, P-O. Okay, here's the crazy thing. Polonium is still unstable and still radioactive. So what we see here when we have radioactive elements is that they constantly are shooting off particles to become more stable, and they continue to do so until they reach a stable spot. And here we see the decay sequence that starts with radium. We started with radium, which we saw in our gold foil experiment. It underwent alpha decay to make radon. And then radon underwent alpha decay to make polonium. Here's the thing, the next decay process is a beta decay. Beta decay. And that will be the topic of our next video. We'll talk about how you can predict the products of beta decay. Okay, so let's summarize. Our alpha decay summary tells us that unstable isotopes are radioactive, and that these radioactive isotopes decay to become more stable. The products of a radioactive decay can be predicted by atomic number and mass number. And then alpha particles always drop the mass number by 4 and the atomic number by 2. Lastly, elements decay until they find a stable isotope. So eventually, this decay sequence that you see on the left ends up with lead, Pb. And that's where it stops. Okay, in the next video, we'll take a look at that beta decay.